Hey, how's it going? Mr. Den here. We're going to start a new chapter, and in this chapter we're going to focus on motion in one direction. Let's go ahead and get started. So the first section we're going to be talking about displacement and velocity, and so our objectives are to distinguish between displacement and distance, distinguish between velocity and speed, and then we also want to be able to calculate the displacement of an object when velocity and time are known, or calculate velocity when time and displacement are known, or calculate time when displacement and velocity are known. Before we get into this, we should talk about a couple things, terms that we need to be familiar with. The first is frame of reference. And so with a frame of reference, we're basically just talking about a coordinate system, so we know where the beginning, where everything is being compared to. And so we would establish an origin, so very much like in math on a coordinate plane, except in this chapter we're only doing one dimension, so we would just have basically the x-axis, and so we'd have a 0 point, and then everything to the right would be positive and everything to the left would be negative. Or we could just give directions as right or left. Now, we can also have motion in one dimension, that is like for falling objects, where it's just going straight up and down. So we'd have an origin, of course, and this would be a y-axis instead of an x-axis. And so this would be, everything going up would be positive and everything coming down would be coming in the negative direction. We could also just simply say up or down as well. The next thing we need to be familiar with is the delta symbol, and many of you may have seen this before, but it's basically just a triangle, and what the delta symbol means change in. So like anything after it is, we're saying change in like time, so initial time subtracted from the final time, or change in position, which we would write that as delta x, and we will be seeing that here in a second. Okay, so displacement, it's very important that we have a good handle on displacement, and we are able to distinguish it from distance. So displacement is basically the length of the straight line drawn from the object's initial position to its final position. And we must also give the direction that this change took place. For example, this drawing here, we have x initial and then x final. And since it's 10 meters to the right, we would report that as change in x equals 10 meters to the right. We could also just, sometimes we just give that as in the positive direction, or we would just say 10 meters. Typically though, we'd like to say right or left, up or down. Now later on, when we get into two dimensions, we will get into things like north, south, east, things like that, and then it gets a little more complicated. Now, based on the using the coordinate plane, displacement can be negative also. But to be honest with you, the negative direction would be left. Okay, distance is the other term that we need to be familiar with, and I think we already know about distance, but knowing how it's different from displacement I think is important. So distance is the total length of the path that an object travels, and so there's not going to be any direction indicated. So for example, on this little drawing I have Alan's path and Eva's path. So Alan's path, as you can see, is very, very curvy. So if we wanted to give his direction, let's say this was 356 meters for that entire curvy path all along here, that would be the distance. However, since he started here and ended here, the distance traveled is going to be different than what we would give as his displacement, and so his displacement is going to only be 100 meters. And so I think it's important that we do understand how, an object can cover lots of distance, but its displacement sometimes isn't very much, or sometimes it's 0. Okay, so and kind of going along with what I was just talking about, we'll just do a quick example of seeing how they're different. So like if we were going to give Eva's distance, and I'm just going to abbreviate that. We'll just put Eva up here. Oh, that's not very good. So her distance, and so going with the definition, the path that she traveled, so it's just going to be 100 meters. And then her displacement, and we'll just use change in x because that's what we use to signify displacement. And so again, the definition of displacement is the straight line from the initial position to the final position, and in this case they are the same. Now Alan and as I said before, and I just made up a distance, is 356 meters, and then his displacement is going to be equal to Eva's because they both started in the same spot and ended up in the same spot. So 100 meters is going to be his displacement. Okay, so two of the formulas that we will use in this unit and in this chapter, and we will have lots of formulas. Now, I don't expect you to have these things memorized, but you should have them written in your notebook, so you might want to press pause and write these down, or you could look them up in your textbook. But anyway, average velocity is going to be displacement divided by time, and this is the abbreviations for that, and it's just easier to write it that way. And then average speed is just going to be the total distance divided by the change in time. And so like in Alan's case, the total distance would be the 356 meters divided by however long it took him to travel that far. If we wanted to find his velocity, then we would take the 100 meters because that was his displacement, and divide it by that same amount of time that it took him to get there. Okay, so let's do our first example problem. So one thing I'd like you to do is when you do these, and on the worksheets I give you a space to do this. So it's a really good idea to go ahead and just identify your givens before you really get into it. And so we're only going to have 3 things involved here. We're going to have velocity, displacement, and time. And so let's just see what we're given. So I'm just going to list these out. Displacement, and then time. And so as you read through this, the fastest fish, the sailfish, can swim 1.2 times 10 to the 2 kilometers per hour. Sounds like a velocity to me. But let's go ahead and read this to finish, and just we'll figure it out after I finish reading it. So suppose you have a friend who lives on an island 16 kilometers away from the shore. If you send a message using a sailfish as a messenger, how long will it take for the message to reach your friend? So the 1.2 times 10 to the 2 is going to be the velocity, and I'm just going to write that as 120 kilometers per hour. And then the change in x was 16 kilometers. And then time is what, whoops, I meant to make a question mark, is question mark. So the formula that we're going to use is going to be velocity equals displacement over change in time. Now, to be honest with you, since there weren't any directions given here as far as right, left, north, south, anything like that, we could use the average speed formula as well. I seriously doubt a sailfish is going to swim in a perfectly straight line. So anyway, so let's just, you could do this a couple ways. You could rearrange for what you're trying to find. So we're trying to find change in time. So we could do that, or we could just plug numbers in where they go. So let's just go ahead and do that real quick. So so we're going to end up with, what do we have? The velocity is 120 kilometers per hour. And change in x is 16 kilometers. And we'll just put change in time here. Okay, so we just have to solve for t, and so if we're doing this algebraically, these two guys will just switch places. And let me get a calculator real quick. I thought I had this already worked out. So 16 divided by 120.13 hours. And so change in time is equal to 0.1 hours. Okay, fairly straightforward. Okay, so let's just do a couple real quick, easy ones, just to kind of also get into the differences in speed and velocity. And this is something I really want you to understand. And on that last problem, that might be sort of contradicting myself a little bit, because there kind of, it said you could use either formula, but there are going to be times when we need to definitely, go with velocity and make sure we give a direction, report a directions. But the main thing that's different is there's a direction involved with velocity, and we're using displacement. So let's just do a quick example of where the technicality is there, and whether or not it's really important or not is debatable. Okay, so sometimes let's do this quick problem. Sometimes the magnitude of speed and velocity are not equal. So if a person walks one lap around a 400-meter track in 153 seconds, what is the magnitude of the average speed and the average velocity? And whenever I use that term magnitude, what I'm talking about is just, the size. And so with the velocity, we won't give a direction. I'm just basically trying to show you how this can be different. So let's just do average speed first. So average speed is going to be equal to the distance over change in time. And so we went 400 meters in 153 seconds. And that's going to come out to 2.6 meters per second. And then if we went to find velocity, and this is going to be average, so I'll put a bar over that to tell you that it's average. And so we got change in x, which is displacement, over change in time. Well, since the person went one lap around the track, they end up in the same spot. So change in x is 0, and the time is 153 seconds. And so velocity is 0 meters per second. So this would be a case where the speed is not the same as the velocity. I know that doesn't fit our everyday experience, but in physics, that's the way it is. Okay, so, and then sometimes they are the same. So let's just do an example of where they are going to be the same. And so, Florence Griffith Joyner set the women's world record for the 100-meter dash in 1988 with a time of 10.49 seconds. What is the magnitude of the average speed and average velocity for her trip? Okay, so we'll do average speed first. And so her distance was 100 meters. And our time was 10.49, and that comes to 9.53 seconds. No, 9.53 meters per second. My mistake. So then let's do velocity, average velocity. Again, since she's going in a straight line, we can use these 100 meters. Her change in x was 100 meters. And the time, 9 seconds. And they will both be 9.53 meters per second. Now I just did that just to show you that sometimes they can be the same. And I know that for some that's going to be a point of confusion. You just have to make sure you pay attention to what is being asked for. But most of the time, the problems that we will do will be just straight line types of things. We won't try to be tricky about it. But there will be occasions where I will throw those kinds of things at you just to see, or to test your knowledge and test that you can distinguish between the two. Anyway, I think that's pretty much it for this section of Chapter 2. So your assignment from here is to do the 2A practice problem worksheet, check your answers. You can do it as you go, or you can do them all and then check. It's probably going to be a good idea to check them as you go, maybe do a couple, check. I don't want you to do a whole bunch and then see that you're not doing it right. And then once you've done that, then you need to do Chapter 2, Section 1, 2A quiz. And then you can move on from there. Anyway, this concludes this screencast. I hope you enjoyed it as much as I enjoyed making it, and I will see you in class.